So this video is going to replace the actual experiment for paper chromatography. So let's get right in and talk about what chromatography is. Chromatography is a way to separate chemical compounds, right? One way. There's several different methods. You can use gas chromatography, liquid chromatography, thin layer chromatography, or even what we are doing here, which is paper chromatography. And what's common to all chromatography processes is that you have a mobile phase and a stationary phase. So let's look at the different methods. So for gas chromatography, your stationary phase is a coated column. There's lots of different types of columns that you can use in a gas chromatogram. And then the mobile phase is gas or a mixture of gases. The liquid for liquid chromatography is a coated columns. It's not the same type of column that you use for gas chromatography, but it is a column that's connected to the instrument. And the mobile phase in this case is a liquid solvent or a mixture of solvents, some type of gradient. Paper chromatography, the stationary phase is cellulose paper. That's the lab that we're going to be talking about today. And again, you have a liquid solvent mixture, some type of gradient, or some solvents mixed in some type of ratio. And then you have thin layer chromatography, in which your stationary phase is a silica coated plate. So that silica can be adsorbed to either glass or plastic or aluminum. And then your mobile phase in this case is a liquid solvent mixture, and it's the vapors from that mixture that kind of give this type of capillary action that move the compounds up the silica coated plate. All right, one of the things that you need to remember are these two uh, phrases: the mobile phase, which is the phase that actually moves, in this case the gas or liquid or mixture, and then your stationary phase, which is the phase that actually does not move. That's the phase where your molecules either pass over or are added to and then allowed to move across it either through capillary action or some type of wicking action or something like that. All right. So paper chromatography is again one type. The stationary phase we already talked about is a piece of chromatography paper that's made of cellulose. That's important because that cellulose is going to help us to determine which compounds would adhere better to the chromatography paper than others. And then our mobile phase for this paper chromatography experiment is a hydrochloric acid and acetone mixture. It's this mobile phase that's drawn up the chromatography paper by capillary action. So when you have a compound that's spotted on the paper, when the solvent passes over the compound, it's going to drag that compound up with it. And I'm going to show you that shortly. And then you have the separation, which is in this case based on different chemical and physical properties. Sometimes it's polarity. And in this case, it might be hydrogen bonding. It just depends on what the compound is that you're trying to separate. And then we're also going to look at calculating the RF value, which is just a simple calculation where you measure how far the solvent travels, you measure how far the spot traveled, and then you take the quotient of the two, and that'll give you what's called the RF, or the retardation factor. And that's good for determining how well a compound adheres to your stationary phase. Right. So with paper chromatography, one of the things to remember is that cellulose has these hydroxyl groups that are on it, and those hydroxyl groups uh, cause metal hydrates, which is what we're going to be talking about later. That's just a metal with a water attached to it as a ligand. That's a hydrate. And so these metal hydrates, when they pass over the cellulose, they tend to stick or adhere to cellulose a little bit better because of what's called hydrogen bonding. And that's this interaction that you see here between the two hydrogens. Hydrogen bonding is one of our intermolecular forces. It's actually the strongest covalent intermolecular force. Right? You have hydrogen bonding, dipole interactions, van der Waals interactions, and then on the ionic side you have ionic bonds, which is the strongest of all of your interactions, all of your intermolecular forces. All right. One of the things to remember for any compound is that if it sticks better to the chromatography paper, if it adheres better, then it's going to move up the paper more slowly. And so we expect that metal hydrates, if it's a metal hydrate, it's going to move up the chromatography paper a lot slower, and it's going to have a lower RF value than something that does not stick to the paper as well. So how do you prepare a chromatography sample? Well, the first thing you do is you draw a 1 centimeter a line across your chromatography paper, approximately 1 centimeter from the bottom of the paper, and then you mark above that line with an X. That's very important, because if you put the X below the line and the compound that you're spotting on the X touches the solvent, it simply gets dissolved and your sample is ruined and you have to start over. All right, so once you put the X on the paper, you have a small amount of your compound to a test tube or a vial, and then you take a capillary tube, dip it into the sample, and then you take that capillary tube or tap it onto the X, right? And as you're tapping it onto the X, the capillary action is going to pull the compound that's in the capillary tube out onto the paper. And then you have to set up a developing chamber. That's what this is. A developing chamber is simply a beaker covered with a watch glass, and your solvent is here in the bottom. And this is where you're going to place your chromatography paper into to be what's called developed, right? As vapors from the solvent move, right, those vapors are moving up, and because they're lighter than air, and since they're moving up, they're also going to drag the compounds that are on the plate, which are here and here. They're going to grab those compounds and drag them up the plate. All right, let's look at that again. So notice you have two compounds on the plate. One of them is moving a lot faster than the other. So what that tells us is that the one that moved really slowly adhered or stuck to this surface a lot better than the one that moved really quickly. That matters, right? Because when you go to measure the RF values, the compound that moved quickly is going to have a higher RF value than the compound that moved very slowly. All right, so here again is the RF calculation. This is an example of a plate, a TLC plate or a piece of chromatography paper. This is where we spotted the spot. This is the spot itself. If we're measuring, we measure from the line where we spotted it to the middle of the spot, right? That's going to be the distance that the spot traveled. And then when we also have to measure the distance from where I spotted the spot to where the solvent stopped, right? That's called my solvent front. When I do that, I get a number here and a number here. So in this case, this would be 7 centimeters, this would be 10 centimeters, and then so my RF calculation would be just the distance that the spot travels divided by the distance that the solvent travels, right? So the 10 would go here, the 7 would go here, and if we would calculate this value, it would be 0.7. All right, we're also going to talk about how to determine an unknown, right? We have a mixture here, and we have several unknowns. If we look at the mixture, we can look at the RF values and compare those to the unknowns to determine which is which, right? So here's the mixture of compounds. Obviously, this spot at the very top corresponds to this spot here at unknown 2. This spot here, the second spot, obviously corresponds to the spot at unknown 3. And then this spot corresponds to the spot at unknown 1. So you really have to use your CSI detective skills in this case. If you had a mixture of compounds and you had 3 unknowns and you had to figure out which was which. All right, you can also visualize chromatography paper. You can visualize TLC paper, TLC plates using UV visualization. You can also visualize using different stains like phosphomolybdic acid or PMA or vanillin or potassium permanganate. In the case of this paper chromatography experiment, we're actually going to visualize using ammonia vapor.